So we were talking about actually. One second.
Actually, what?
So my net is a bit. Yes, so one second. So actually, we were talking about Turing machines and Turing recognizability, sir.
Okay. So I started with the age-old language onion, and and I was talking about three specific classes of languages for which you actually need a machine, not very complicated, not more complicated than, not much more complicated than finite automata or PDA, but enough, but 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 it has enough power to actually define or actually work with three specific language classes, and those language classes were decidable languages, Turing recognizable languages, and even languages that are not Turing recognizable, right? And I also talked about that in order to deal with these three specific language classes, you need a machine that that is capable enough to deal with such languages, right? Is it? What were decidable languages? By the way, do you remember? With what other names
Yes,
do we
sir.
call decidable languages?
So recursive.
Yeah, recursive, right? Or we can say solvable, or we can say computable, right?
Yes, sir.
Yeah. So when I say solvable or computable, actually I don't talk about languages, right? Because from the sense of the terms, I am talking about problems. Solvable language is not a particular good usage of the term, right? Computable language is neither. But recursively defined language is a good term. So when I'm talking about solvability or computability, I, I, I primarily indicate to problems, category of problems. So how do I relate problems to language classes? So there is a very interesting point to note. You just note, because in today's class we are not going to delve into those complexities. Actually, what is meant is all problems that are solvable and computable, or solvable or computable, can be encoded in a language that is a decidable language. That's the beauty, right? So now I come to the actual beauty of encoding problems in terms of languages. And then to check whether the problem is solvable, whether the problem is computable or not, we design a machine to accept that language. That in turns says or proves that, okay, if a particular problem, if a problem is at all solvable or computable, and if that problem, all instances of that problem can be encoded in a specific language, that language becomes decidable if and only if the problem was solvable, right? And if it is decidable, then we can think of a machine like we talked about machines in case of finite automata and pushdown automata. We can think about another machine that is capable enough, that is powerful enough to decide on such problem instances as encoded into languages, right? So Turing machines uh, actually target this class with its maximum capability. We say that Turing machine is a machine. We have defined Turing machine formally, and we have also seen examples. This is just a recollection. Certain things need to be talked about multiple times such that concepts become absolutely clear. So Turing machine is a machine uh, we will define decidability of languages, and then in turn talk about solvability of problems in a way in terms of Turing machines, right? That is what I mean, in terms of Turing machines. So we'll say that a Turing machine can decide such languages that in turn reflect to solvable problems and their encodings, right? And then we talked about the Turing recognizable languages, and we also talked about non-Turing recognizable languages. So in terms of Turing machine, what is a decidable language? How did we define a decidable language? So we say that given a string, given an arbitrary string as input, if that string belongs to a particular language that is decidable, then the Turing machine will always accept it and halt its computation. Right? By the way, if we go back to the last class, and if you can try to visualize what I talked about, a Turing machine is a pretty mechanical machine, right? With a tape head that was allowed to move left, that was allowed to move right, and even allowed to stay stationary. And even added to that, symbols, you were allowed to erase symbols and write new symbols, right? So that bunch of mechanical operations, uh, if that bunch, if a specific bunch of mechanical operations involving the left, right, or stationary movement of a tape head and a read or write action on a tape symbol, input tape symbol, and if those bunch of operations actually end the computation while exhausting that particular string, if that string W is a member of a decidable language, then the Turing machine always halts, right? Accepts and halts. And if any arbitrary string that is not a member of a decidable language, then also the Turing machine always rejects and halts. So both of the decisions, whether W is a member of a decidable language or not, whether W is a member of a decidable language, or whether W is not a member of a decidable language. By DL, I mean a decidable language. If we talk about DL as a decidable language, then the Turing machine always accepts and halts in case some W, the given W that the Turing machine computes on, this given W is a member of DL. If it is a member of DL, the Turing machine will always accept and hold. If it is not a member of DL, the Turing machine will always reject and hold. This always term is very interesting, right? It needs further discussion. What I mean by always in terms of encoding of problems, just now what I told was any problem that is solvable and that is computable can have a encoding, can be encoded in a language form, right? So we say that so if a problem can be encoded in a language form, then a string W can be considered as an instance of the problem, right? Instance means instance of the problem. It means that a problem with specific inputs, right? So if we say that if we say that if W, so what I mean is, by decidable languages, if I define decidable languages in terms of Turing machines, this is what I mean. That if DL is a decidable language, then given any string W, if that W is a member of the given decidable language, then a Turing machine will always accept and halt for all instances. If it is not, the Turing machine will always reject and halt for all instances. That means the Turing machine is capable of deciding whether a particular string W is a member of a language or not. And if it actually decides on all such strings for a class of languages, then that class of language is called a decidable language. So I have now successfully defined decidable languages in terms of Turing machines, right? So what about Turing recognizable languages? Turing recognizable languages say that if W is a member of a Turing recognizable language, then there is just a Turing machine that always accepts and halts. But if W is not a member of a Turing recognizable language, then the Turing machine may not always reject and halt. It may go to a loop. It may loop indefinitely if it is not a member of L. So if we want to define Turing recognizable languages, don't go by the name. The name is a bit of self. It's a bit of don't go by a name. Let it be a language. So there is a class of languages for which a Turing machine recognizes a string W if it is a member of L, if it is a member of some particular language, but it cannot decide on that. Here it was deciding whether yes or no, the membership, whether this membership was yes or the membership was no. Here it cannot decide, but it can only recognize if it is a yes, right? It only recognizes the yes cases. So having defined a language in terms of Turing machines like this, we define that language as Turing recognizable languages, right? Also, there are languages that are that should be very unpopular with computer science people, are languages that are not even Turing recognizable. So even if there even if some W is a member of some language, there is no guarantee that the Turing machine will that there is no guarantee that the TM always accepts and holds, right? Also, if W is not a member of a particular language, there is no guarantee that the Turing machine always rejects and halts. I can give you examples of such languages, but later on, because that needs a better insight into the subject. So these three classes of languages, these three special classes of languages, actually they are not special. I can include them in the language onion. I will show you. These three special classes of languages, decision problems, these are actually decision problems. Decision problems on these three special class of languages. For that, you need a Turing machine, right? I think I'm writing on some old board, so I should be changing a board. That's why my pen is hanging. Okay, I got it now. Okay, so having said that, I can draw the language onion to look something like this: regular languages, context-free languages. Then you have decidable languages, DLs. Then you have Turing recognizable languages. And then you have, for example, I can fill up this with the universe, non-Turing recognizable languages. So this portion is decidable languages are recursive. Turing recognizable languages are also called um, um, recursively enumerable. Right? So this to take a decision on whether you need a machine as powerful as Turing machine. So to say, I can also include a subclass for which I do not need the full-fledged power of Turing machine, but that's essentially a Turing machine. But we do not need the full-fledged power of Turing machine, and we can limit the playing place of the input string where we manipulate and proceed in the linear order of the length of the input itself. And that is some sort of Turing machine with linear bounds, and that is called linear bound automata. And that is a specific um, machine corresponding to context sensitive languages. But that actually is a Turing machine, right? A Turing machine, a linear bound automata is nothing but a Turing machine bound by some linear factor of the input length, right? So this is what I mean. So we should be happy that context free languages and regular languages that has direct applications to computation that are decidable. We should be happy with that. Okay. Okay. So let's come back to
what linear bound automata is, sir.
Okay. So we have, so look in the language onion once more. You have the regular languages at the core, then you have the context free languages, right? So I have intentionally not mentioned the LLK and the LRK cases here, right? I have not mentioned, right? To keep things simple. So now I built a hierarchy with regular languages, context free languages, and uh, and decidable languages, right? Decidable languages encompass CFLs, and CFLs in turn encompass regular languages. So here we actually need a Turing machine, a machine as powerful as a Turing machine, to have a decision on such languages. This portion, right? Got my point? But we can also say that there are a particular class of languages that I can say that is not a CFL, that is decidable, but that is not a CFL, but that can be decided. This portion, okay, let me color this up. This portion. So there is not a CFL. It's a decidable language, but this is not a CFL. Some different sort of language, but that doesn't need the full-fledged power of a Turing machine to decide upon, right? Got my point? So that subclass of decidable languages, but not CFLs, that class, this green portion, which is not CFL but decidable, doesn't require a full-fledged Turing machine for taking decisions on that language, right? Got my point? And that portion can be classified. As a machine called linear bound automata. That is nothing but a Turing machine with linear bounds. Linear bounds means if the size of the input is n, then the problem can be solved with the input tape size of m dot n. Got my point? So if the size of the problem is, say, if the size of the problem is if the size of the input string is 10 symbols, then this green portion can be solved with say 2 into 10, that is 20 cells on the input string. Right? It can be solved with 3 into 10, 30 cells on the input string. We do not need an infinite input tape to solve the problem. But here we have problems. But here, let me color it with, say, orange. In this portion, you have problems that actually require a full-fledged Turing machine to solve, right? That means you have a tape that is infinite towards the right. You need that. So the number of operations on the input tape, the number of head movements, the number of times you need to erase a symbol and write a symbol may not be linearly bounded with the input size. Got my point? Is it clear or not?
Yes.
Now, actually, this linear bound automata, this green portion, is a Turing machine with linear bounds. So that's why I didn't teach you linear bound automata yet. My idea is to talk about Turing machines and then talk about LBA. Things would become easier, right? And LBAs talk about a specific class of language called context-sensitive languages. You know this class of languages. One example being the very popular 0N, 1 and 2N. Right? We know that this language is not context-free. So this is this green portion. It belongs to this green portion. Right? And this language is not context-free. But to accept this language, you do not require a full-fledged Turing machine with input tape infinitely open towards the right. This can be solved with, for example, this is n number of zeros, n number of ones, n number of twos. So you have 3n number of symbols, right? Right? So it can be well solved with some linear number of 3n, for example, m dot 3n. So we can have, we may need 6n number of cells to solve this problem. The input is 3n, n number of zeros, n number of ones, n number of twos. And we may require another 3n number of cells to manipulate, right? We may move right, we may move left, we may do whatever we need to do. This language, you are accustomed to this language. Got my point? Yes or no? Agreed?
Sir.
Yes or no? I will only proceed if I hear a yes.
Yes, sir. Yes, sir.
Yes. So pulling threads from your finite automata classes, we graphically represented transitions like this. We are in some state Q. We change state to P if we see a input A. This was the finite state machine model, right? The graphical representation. What was the PDA? PDA was something like you are in some state Q. You go to some state P. And how do you decide to change a state from Q to P in case of a PDA? You read a input symbol, you read the top of stack, and what you do is you decide to push a symbol on the stack by reading the top of stack, right? Let it be B. So B was pushed on the stack, and you change state from Q to P by seeing an input symbol and the top of the stack. This was PDA. And with the same notation, such that things remain simple, we talked about the Turing machines, that Turing machine that looks something like this. We are in some state Q. We change the state to P, and we read a symbol A from the input tape, and we rewrite that symbol A by a symbol B, right? And we either move left or remain stationary or move right in the tape. This is how I related all the three things, right? Yes? Yes or no?
Yes, sir.
So so in case of PDA, we told that each of these can be epsilons, right? And we had two detailed classes. I am not going into those. That made a PDA a non-deterministic, especially if you were allowed to not read the input and have a transitions. So especially if you have an epsilon in place of A, right? Similarly, in case of Turing machines, it can be done. But I ask you a more intuitive question. What if you don't want to update a cell? What if you don't want to erase A and write a B in place of A? So a very simple transition can be, you are in Q, you can change a state to P without actually rewriting A. That means you are rewriting A with a A. That's the concept, right? Don't get confused. So actually you are not changing the symbol. So this implies not updating a cell. That means I'm rewriting the cell with the same symbol, that is scanned. So I scanned A, I rewrite A by A, right? And then I decide to move left or to remain stationary or to move right. Now see, from the basic definition and transition patterns of these three machines, a Turing machine is not very complicated than the PDA, right? It is also not very complicated if compared to the FSM. And it has exactly the same way of representing things that you can do. You also represent the same things. Q cross the tape alphabet was taking you to Q cross the tape alphabet cross the head movements. It may be left, it may be stationary, it may be right? And you also can define a non-deterministic degree machine by using the power rule, right? 2 to the power Q cross tau cross L S R. So I prefer to use unified description such that things become easy. So this was a Turing machine that I talked about in the last class. So for the whole 40 minutes, I talked about what I talked in the last class, but that was required. Sometimes repetitions are required so that concepts become absolutely clear, right? Okay, let's now solve a problem with. Um, okay, before that, what should be the acceptance and reject criteria of a Turing machine? What we mean by accept? For a Turing machine, without using the term accept and reject, we would prefer to use something like to make things more in line with the way the machine was actually defined by Alan Turing. It should be halt and accept, and it should be halt and reject, and the other option is loop. If you relate to just now what I talked about 15 minutes before, all these three conditions are actually determinants of a decidable language, a Turing recognizable language, and a non-Turing recognizable language. Right? So halt and accept. So what is halt and accept? Whenever the Turing machine enters an accept state, the computation immediately halts. So halt and accept is better said accept and then halt, right? You should remember like this. So whenever the machine goes into some accept state, so whenever the machine goes into some queue, there is a member of accept, then the machine immediately halts and stops computation. Similarly, you define as reject. So whenever the machine enters the reject state, it immediately halts. Right? And what is loop? The machine fails to halt. So if I say that accept and immediately halts is halt and accept, reject and immediately halts is halt and reject. And if I say that looping is failing to halt, I actually mean that it fails to halt because it fails to either accept or reject. That is why it fails to halt. Because if it was accepting, it would have immediately halted. If it was rejecting, it would have immediately halted. Did you find the logic in the definition? So there I say that it fails to halt, that I define looping as something like quote unquote fails to halt. I actually mean that it fails to accept, so that it fails to accept, and so it loops. It fails to reject, and so it loops. That I say it fails to accept and it fails to reject, I mean it fails to accept and it fails to reject in polytime. You're studying algorithms, so you should be knowing polytime in finite time. Yes or no? Yes.
Yes, sir.
And since it is easy to think about halt and accept and halt and reject and loop are the three determinants of determining uh, 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 decidable language, Turing recognizable language, and languages that are not even Turing recognizable. That's why I defined a tuple q sigma tau, then del, then q accept, and then q reject, right? Do you remember? So if you have dedicated accept states, if you have dedicated reject states, it is easier to have a definition like this, to have a direct correspondence to definitions like this. But as I said, there are books that prefer to define a Turing machine like Q sigma tau del, then a blank, and then Q accept. And they don't talk about the reject state. This is also an equivalent definition. But using this definition, it is tougher to visualize these three conditions, right? That's why I used with a tuple definition like this. But this definition also inherently means that if there is no transition out of a state defined, it actually goes to some state called a reject state, right? A sync state. So it doesn't really matter how you are defining your tuples. I prefer this way because it has a direct correspondence to your defining things, right? Got my point? Okay, so let's come back and have an example. What example shall I take? Okay, let us take the example of 0 and 1. Right. Now, you have a prerequisite knowledge that this language is a context-free language. But if you go by the language onion, if some language is context-free, that language is decidable, and so if it is possible for you to design a push-down automata for such a language, it is always possible for you to design a Turing machine for the language, right? Yes or no? I'll only proceed if I see if I
Yes,
go
sir.
to
Yes,
yes.
sir.
Yes. So let us see an algorithm or some steps to use a machine that is bounded on the left and that is infinite towards the right, and there is a tape head at a single point of time scanning a particular symbol in the input, and the input is, for example, say 000111, right? So this is the input, and so at some time t your configuration looks like this, and this is your finite control, right? So what should be the algorithm to accept such languages? So this is a sample string. If you remember, this is w, and to check whether w is actually an element of L or not is a decidable problem. Why? Because we know this is a context-free language. So of course, context-free languages are contained within the class of decidable languages. So the very question whether this w is an element of such L is a decidable problem. So that means we can always have a Turing machine that accepts and holds. Done. So I related everything. So what should be an algorithm to 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 check this using this machine structure? What should be it? Pretty simple, right? For example, you scan a 0 and you move past all zeros. You scan a 0. So this is the initial configuration. The head is scanning the leftmost symbol, and what you do is you scan a 0
Press the 0 for the 1.
and please turn off your microphones. You scan a 0 and then you move past any 0 that you find, and you rest your head on the first one that you find. Done? Yes or no? Then you should be coming back. Then you should be coming back. And you should be coming back to the second 0. But how to decide that you come back to the second 0? Because by this time, when you come back, you may accidentally come back to the first 0 that you had already seen. So the algorithm is, once you see a 0, you mark it with X, a special symbol, and move past all the zeros until you see a first one. If you see a 1, you mark it with Y. Then come back until you see a X. You come back left until you see a X. See a X. If you see a X, turn right and scan. If it is 0, mark it with X. Skip past zeros and Ys. Skip past zeros and Ys and check whether you land to a cell that has a 1. Mark it with a Y. Then skip past Ys and Ys and come back until you find the x. If you find the x, you turn right and check whether it's a 0 or not. If it's a 0, you mark it with the x. And after marking with an x, if you don't find any other zeros but only y's, you skip all the y's and expect to find a matching 1 with respect to the last marked 0, right? And mark it with a y. Yes or no? Yes? So
Yes,
by
sir.
this time, yeah, so by this time, all the 3 zeros and all the 3 ones should have been marked, and you should be expecting a blank. And once you see that blank, the computation ends. So how to represent that with the graphical notation? Okay, so let me find out a graphical notation for this. So you start in some Q0, and here there are so the language is, see, the language is 0 and 1 in, right? So n, if n is greater than equal to 0, you should be actually accepting epsilons, right? But if it is greater than 0, then if n is greater than 0, then the strings essentially start with a 0. There is no scope to start with a 1 because the language is 0 and 1. Yes or no? So you have two options in Q0. Um, one is if you get a blank, and one is if you get a 0. Very simple, right? So if you get a 0, you mark it with an X and move right and change your state to some state Q1. In Q1, what you do is you have already moved right, and you have changed it to Q1. So after moving right, the next cell after the first 0 that you have seen, maybe a 0, right? So if it is a 0, you override that 0 with a 0. That means you ignore changing symbols and move right. And another option may be that after seeing the first 0 and moving right, you may be seeing a y, right? This option. After seeing a 0, you may be seeing a y. So if the string is 0, 1, after seeing a 0, you should be waiting for example, um, I take this example, that 0 0 0 1 1 1, and at some point of time you have seen a um, y that has a sum 1 that has been converted to a y, right? Sum 1 that has been converted to a y. Let all the zeros have been converted to x, and leaving only 1 0. So you see this 0 and you see a y after moving right. So if you see a y, you ignore seeing what you see and rewrite that y with a y and turn right. So that is what you do in Q1. So in Q0, another option is you can get a blank, and if you get a blank, you should be accepting that blank, right? Because actually you should be accepting um, epsilons, right? So blank stationary, and this may be some Q accept. So Q1 is very important. In Q0, what you do is you find a 0 and move right. You override that 0 with a x and move right. After moving right, you can see a 0. After moving right, you can see a 0. Or after moving right, there is also another option of seeing a y. And this option you have to visualize as some intermediate option, some intermediate portion of the computation, right? And from Q1, you see a 1, replace that 1 with a y, and what you do? What should you do? After replacing that 1 with a y, you should be immediately moving left, right? You should be immediately moving left until you see what? Until you see what? Until you see a x, right? And in moving left, you need to skip past zeros and y's. In moving left, you can see a y. If you see a y, you replace that y with a y and continue moving left. If you see a 0, because you are moving left, you can see a 0. you need to skip those zeros, right, and continue moving left in this state Q2. And in this state Q2, by moving left, where should you go? You should come back to some state where actually you find the X. Now, once you find the X, you do not decide to override that X with some other symbol and move right. That is actually what I explained here. If you remember, I will explain it once more, right? And after you turn right, there is an option that in this state you can find a Y, right? So if you get a Y, you replace that Y with a Y and turn right. Then you should be coming back to some state called intermediate state Q3, say, and here you have to skip past all the Y's. And this is a situation where all your ones have been converted to Y's. This situation is displayed by Y arrow Y comma R. And then you actually accept with a blank. So blank, blank, and stationary. So that is what I mean. So let me have a correspondence with this picture. Let me zoom out a bit and let me explain once more. So this is what you have: 3 zeros, 3 ones, right? So what was the idea? The idea was, once you see a 0, you start here, right? You start here. So you are at Q0. So you are here, right? So you see a 0, you mark it with a X and move right. Mark it with the X and move right. Moving right, I change my state to Q1. And here I see a 0. This is one option. So I see a 0. I continue moving right. I see again a 0 and continue moving right. Now, if I see a 1, I replace it with a Y. If I see a 1, I replace it with a Y and move left. Right? And moving left, the only possibilities are I see a 0 or a Y, right? Because if you had been moving left from some point here, you would be seeing Y. I would explain. So I am seeing a 0 now and moving left. Seeing a 0 moving left in Q2. Moving left. And now I see a X. Now once I see a X, I move right and go to Q0. Once I see a X, I move right and read the next 0 from Q0, right? I see things from Q0 now. In Q0, I see a 0 again. So I mark it with an X and move right, right? In Q1, I skip this 0 by virtue of this production. And I skip a Y by virtue of this production. Now you can see that YYR was there in Q1. So I need to skip this Y also because I'm in search of a 1. And once I see a 1, I apply this rule and mark it to a Y and turn left. Now when I'm turning left, I need to skip Y's and zeros. I need to skip Y's and zeros and rest to a X. And once I find a X, I have to move right and rest on the next 0. This is the algorithm. And this is the pictorial representation of the machine. Now, are things clear? Yes or no?
One doubt, sir, like actually from the figure only, sir.
Yes.
So that Y,
Yes. Is it
Y
because
arrow,
one
Y.
minute? Is it because of my bad board work?
Sir, no, actually, sir, I am not getting whether it's a
Yes,
transit,
yes,
like
yes, yes.
transition
Your
or not, sir.
question. Your question. Your question.
Sir, if it's Y arrow, Y L, sir, sir, which transition is that for
Y,
from Q1 to Q2?
Y arrow YL. Okay. So
Yes.
see, yeah. So see. Okay. Good question. I am happy whenever you ask me questions because that's the only option when I'm forced to think, right? And it is your duty to make me think and answer. So let you are here. You have marked a 1 to a Y. Are you listening to me? You are listening to me?
Yes, sir. Yes, sir.
So let just now there was a 1 and you have marked a 1 with a Y. Right? So you need to skip past the Y that is on your left. So I turn left and find a Y. So if I find a Y, I don't convert that Y to something else, but rather what I do is I I skip past that y. So y, I see a y, I keep that y, that means replace that y with a y, that means I keep that y and move left. So this is skipping past. So I turned a 1 to a y and then I turn left, right? I turned a 1 to a y and then turn left. Okay, let me explain it. So this is the situation in some intermediate computation history, right? So you started with, let me draw, let me not be lazy, right? A bit lazy. Let me not be lazy. So I started here 0, 0, 0, 1, 1, 1, and we had some finite number of computation steps, right? And at some point of time, you are in this place. You have marked two x's with a 0, and you have just now marked this one with a y. Got my point? Now, once you have marked this one with a y just now, what you have to do? Your idea is to move left until you find a x, because x is the marker. And once you find a x, you have to turn right to look out for any other zeros, right? So for doing that, you need to skip past any y's, right? Got my point? You need to skip past the y's that you see moving left. So you have changed this one to a y just now. Now you turn left and find another y. So you need to skip past that y. So y left. What does that mean? I'm skipping past this y and going left. Now I find a 0. I should be skipping past this 0 also, right? And turning left in search of a x. So once I find a x, I stop. I change state. And I try to return back to some initial position where I started scanning the zeros, right? So I go back to Q0 again. So once I see a x, what I do is I straightforwardly go back to Q0. So x, and sorry, I gone back to the PDA notation. So so if I see a x, what I do is I simply um, find that I have reached the position where the last 0 was marked an x, right? And I move right. That means I'm ignoring that x. How to ignore x? Um, I mean that I see a x and override that with an x only, right? So x, I find a x, I move right, and now I find a 0. So I am in that sense in the initial state where I started with a 0, right? Now I mark it with a x and move forward. Now I need to skip the y's in search of a 1. Once I find a 1, I have replaced it with a y, right? Now I move left. So again, there is a question of skipping past these y's, right? And you skip past those y's by y goes to y comma l. Got my point? Yes or no?
Yes, sir.
Done?
Yes, sir.
Yes. So that ends today's class. How boring was it, by the way?
Sir, it wasn't boring, sir.
It wasn't boring. Thanks. Okay, let us meet. Can we have a class tomorrow? Yes, Abhishek. Can we have a class tomorrow?
Sir, I don't think Abhishek is in the class at the moment.
Oh,
sir.
he has left. So who
Sir,
is talking?
so this is Projector, sir.
Prajata. Can we have a class tomorrow? Or you'll be enjoying the weekend?
Sorry, sir, I have not left, sir.
Okay.
My-
So you think, is it possible to have a class tomorrow or not? And then Basu will let me know, right?
Yes, sir.
Okay. Okay. So bye for now.
Thank you, sir.
Thank you, sir.
Yeah.
Thank
Yeah.
you.